Welcome back, calculus friends. This is AP Calculus section 4.2, day 1 and day 2 notes. Today we're going to be changing gears and we're going to be talking about maximum and minimum values of functions. And so there are two different types of maxes and mins that we discuss. There are what we call global, or absolute is another word for global, so you might want to write absolute there. I wrote it in red above global. And local. So it means exactly what you would think it would mean. Absolute means the highest value or the lowest value within a given interval, whereas local maxes and mins mean it's the lowest value around an area or in a region based on surrounding values. So when we think about something being an absolute maximum or an absolute minimum at some point C in a given interval D, what we are saying is that in that given interval D, that x value, x equals C, gives us the highest point in the interval. That is how we define an absolute or a global maximum. And a global minimum is some value along your x-axis, again, x equals C, that gives us the lowest value of the function in that interval. And these maximum and minimum values are called the extreme values of the function. They are the highest point or they are the lowest point. Now, a local maximum or minimum is just defined as some point C that produces a function value that is higher than points on the left side and the right side of it. So you can imagine that you could have multiple local maximums and minimums in an interval, but you could only have one absolute maximum or absolute minimum in an interval. And if we take a look at the picture that's provided here, you can kind of see we've got this blue function that's drawn, and we have a couple of locations that are identified as local minimum. Right here we have a local minimum. And by definition, it is a local minimum because if you were to plug at x equals 4, if you were to plug an x value less than 4 in or an x value greater than 4, the value of the function would be higher at those values than it is at 4. And at x equals 8, you can see that we have a local maximum. So if you were to plug x equals 7 in, the value of the function would be less than what it is at x equals 8. And if you were to plug x equals 9 into the function, the value of the function would also be less than it is at x equals 8. So those two represent the idea of being local maximums or minimums. And again, we can have more than one local maximum or minimum in a given interval. Now, the absolute maxes and mins, well, there can only be one in an interval, right? So if we look here, we kind of see that if this is where our interval begins and this right here is where our interval ends, we can see that this point right here at x equals 1, that is going to be our absolute maximum. That is the highest point in the interval. And by definition, you do not have to be able to see both sides of an endpoint to call it an absolute maximum or minimum. Okay, so endpoints can be absolute maxes and mins. However, endpoints cannot be local maxes and mins because it says right here that in order to determine a local max or min, it must be testable from both sides of C. So endpoints of an interval can never be local maximum or minimum values because if it's an endpoint of an interval, then we're only able to test one side of it. Okay, and so I really want to call attention to this. Endpoints of intervals can never be local max or min values by definition. Okay, they can only be absolute maxes and mins. Okay, so endpoints cannot be local maxes and mins, but they can be absolutes. So when we look at, again, this picture of this function that we are given, we can see that we have an absolute maximum at x equals 1. We have a local minimum at 4. We have a local maximum at 8. Right here at x equals 12, this is the lowest point of the function within the given interval from, it looks like, x equals 1 to about x equals 14. So we would say that that point x equals 12, that is both a local and an absolute minimum. And then the point right here at the end point of the interval, which looks to be about x equals 14, it's definitely not an absolute max or min because it's not the highest point or the lowest point, and we can't call it a local minimum or maximum because we can't see the other side, right? And if we can't test both sides, it can never be a local max or min. Okay, so again, we have a note here. A value can be both an absolute and a local max or min. And some curves may have no max, no min, neither a max nor a min, right? And we have two examples here. Our first example, we have a parabola, and a parabola has no maximum, right? Its minimum is its vertex, but it has no maximum because both sides of the parabola just continue on up forever to infinity. And then the second picture, we have our y equals x cubed, our snake-shaped graph. This has no maximum and no minimum, right? Because it continues on to negative infinity on the left side and to positive infinity on the right side. So we can't say that it has a maximum value or a minimum value. This brings us a discussion of the extreme value theorem. And the extreme value theorem, I think, is a very easy theorem to understand once you have an idea of what maximums and minimums mean in terms of a function on an interval. And the extreme value theorem says that if f is a, number one, continuous function on a, number two, closed interval. So those two things have to be stated at some point. F has to be continuous, and the interval that we're looking at has to be a closed interval, including endpoints a to b. Then f has an absolute maximum value and an absolute minimum value at some numbers in the interval a to b, right? That has to be true. So we've got three different examples here that kind of illustrate this. In the first example, you can see that we have an absolute maximum value there and an absolute minimum value there on the interval a to b. In the second example, you can see that we have an absolute maximum value there at C, and our absolute minimum is also the end point there at B. And then in our third example, you can see that we have a tie, right? We have 2 points where our function is at that same maximum value, and then we have a point here at D where it's at its absolute minimum value. And then in that case, the endpoints aren't anything because they aren't absolutes in this case, and they can't be locals. In the next example, A and B, it says, for each of the numbers A, B, C, D, R, and S, state whether the function whose graph is shown has an absolute max or min, a local max or min, or neither. So again, we have to go back to what the definitions are of absolute versus local. All right, we know that endpoints can only be absolute, they can't be local. Okay, that's the first thing. And we know that by definition, an absolute max or an absolute min has to either be greater than or equal to or less than or equal to all points in the interval. And a local min has to be greater than or equal to or less than or equal to all surrounding values. All right, so for letter A of letter A, I guess, when we look at the graph right here, this is one of our endpoints. So the only thing that it could be is an absolute maximum or an absolute minimum. Well, when we look at the curve, it is definitely not the highest point, and it is definitely not the lowest point. So therefore, A is none. And our reason for this is it can't be a local max, right? It would be higher than the points, but we can't see the other side of the endpoint, so we don't know. We can't call it a local max because we can't test the left-hand side. So it has to be a none. Letter B. Letter B would be considered a local min, because if we test a value less than B, the value of the function would be greater, and if we test a value greater than B, the value of the function would be greater, right? So if we look at both sides are higher, so that means that B is a local min. Letter C. It is not the highest point, so it's not an absolute, just like, B was not the lowest point, so it was not an absolute. But C is a local max, because we can see that it is greater than points on the left side and the right side of the point. Letter D, well, that possibly might be some sort of a point of inflection, but other than that, as far as maximum and minimums are concerned, letter D is none, right? It's not a local max or min. It is not an absolute max or min. Letter R. Letter R appears to be the lowest point of the curve on the interval from A to S. So we would call R both a local and an absolute min. Right? We are able to call it a local min because we can see that it is lower than points on the left side and the right side, but it is also the lowest point in the interval, so it is also our absolute minimum. And then finally, S is an endpoint, so the only thing that it could be is an absolute max or min, and S is indeed the highest point that we see on the interval, so S is going to be our absolute maximum. All right, let's take a look at the picture for letter B. Letter A right here is an endpoint. So again, the only thing it can be is an absolute. And if we look at the picture, we see that the value of the function at x equals a is the lowest point on the figure, right, for the function. So we would say that letter A is an absolute minimum. Letter B, now this is a little bit tricky because we have a jump discontinuity here, right? So for letter B, we have to look at both parts here. And the question is letter B, and again, we have to look at where the closed circle is, right? The closed circle is up at the top. And so letter B in this case would represent a local maximum because points that are less than B or on the left of B are lower, and points that are on the right of B are lower. So B would be a local max. And we would say points on left and right are both lower. All right. Letter C. Okay, now this one is also tricky because here, this is the value of C. It's where the closed dot is, right? So could letter C be a local maximum? Well, values on the left side of C are higher than C. So no, C can't be a local maximum. Values on the right side are lower, but values on the left side are higher. Can C be a local minimum? Well, no, because values on the right side of C are smaller than C, so it can't be a local minimum. And we can't call it an absolute anything because it's kind of right in the middle as far as height goes on our graph. It's not an absolute maximum or minimum. So letter C is a none, is a neither, whatever you want to call it. Letter D, right here, it is not the lowest point on our graph, but it is lower than points on the left side of it and on the right side of it, So letter D would be a local min. Letter R is the highest point of our function in our interval. And it is testable from the left side and the right side. We can see that it is higher than points on the left and on the right. So letter R is both a local and an absolute maximum. And then finally letter S. Okay, well letter S is not the highest point on our graph, and it's not the lowest point on our graph. And remember, because it's an endpoint, it can only be an absolute maximum or an absolute minimum. It cannot be a local. So since it's not the highest point or the lowest point, S is none. And again, this is because it can't be a local. So hopefully these two examples give you some idea of, by definition, what we consider to be an absolute maximum or minimum versus a local maximum or minimum. The next thing that we're going to talk about is Fermat's theorem. And Fermat's theorem says that if f has a local maximum or minimum at C, okay, and if f prime of C exists, so if you can take the derivative at C and the derivative exists and you get a value, then f prime of C is 0. Okay, so that should make sense, right? Because if we have a local max or min, that means we have a turning point. And if we have a turning point, that means that the value of the derivative should be 0 at that location. But it says, note, the converse of Fermat's theorem is not necessarily true. Functions may have locations where f prime of C is 0, but that location is not necessarily a maximum or minimum value of the function. Okay, and to illustrate this, we have two pictures here on the right-hand side. The graph of y equals x cubed and the graph of the absolute value of x. You can see that they both have locations where the function has a minimum value. Okay, x cubed has a local minimum at 0 because it is either lower than or the same as values on the left-hand side and the right-hand side. Okay, and absolute value of x has a local minimum at x equals 0, but f prime of 0 does not exist for that location because we know we can't take the derivative at a pointy point, right? So Fermat's theorem is kind of a one-direction theorem only. It can't go both ways, okay? Just because a function may have a location where the derivative is equal to 0, that may not necessarily be a maximum or a minimum value of the function. So Fermat's theorem suggests that we can start looking for extreme values of a given function by looking at C values, or values along our x-axis, where the f prime of C is 0, or where f prime of C does not exist. And these values are called the critical numbers of a function. So in example 2, they want us to sketch a graph of a function f that is continuous on an interval from -1 to 5 and has the following properties. So in example A, we want it to have an absolute minimum at x equals 2, an absolute maximum at x equals 3, and a local minimum at x equals 4. So the first thing that we're going to do is we're going to create a coordinate plane. And on our x-axis, we're going to go from -1 to 5. And again, we want our function to have an absolute maximum at x equals 2. Oh, sorry, absolute minimum at x equals 2. So we want the lowest point to be at x equals 2. We want the highest point to be at x equals 3. And we want to have a local minimum at 4. So not as low as the value of the function at 2, but definitely lower than it is at 3. And the interval that this function lives on is from -1 to 5. So we know that if we have our absolute minimum at 2 and our absolute maximum at 3, then the endpoints of our interval can't be lower than 2 or higher than 3. They have to be somewhere in between. So how about if I say that it starts there and it ends there? And if I just connect this like this, there we go. I have just produced a sketch of a function that is continuous on the interval from -1 to 5 and meets the given criteria. An absolute maximum at 2, right? This right here is definitely the lowest point on the graph. An absolute maximum at 3, that's definitely the highest point on the graph. A local minimum at 4, lower than points on the left side and the right side. And the endpoints are nothing because they are not our absolutes in this case. All right, for letter B, let's create another coordinate plane. Still going from -1 to 5. And this time, F has no local max or min, but 2 and 4 are critical numbers. Okay, so no local max or min means that our graph can't have any turning points. That says no TPs, no turning points, right? Our graph cannot have any turning points if it has no local max or min. But 2 and 4 are critical numbers. So we have to have a 0 slope at 2 and 4, but we can't have a turning point. So we have to be basically always increasing. So I'm just going to put a dot at 2, and I'm going to put a higher dot at 4. And I have to show that between -1 and 5, I'm always increasing, but yet I need like a leveling off spot at x equals 2 and x equals 4. So maybe my function starts down here and it's increasing and then it levels off and then it's increasing and then it levels off and then it's increasing. So the point is that there's a critical value here. The slope is 0, but it doesn't switch from increasing to decreasing or decreasing to increasing. The graph is always increasing on the interval from -1 to 5. Okay, so we do have critical values here. We have 0 slopes right here and right here, but we don't have turning points there. The final part of the notes today talk about a process that in calculus we refer to as the closed interval method. If we are trying to find the absolute maximum or absolute minimum values of a continuous function on a closed interval, we know that this is either going to happen at a local extremum, which means it occurs at a critical number, or it'll be one of the endpoints of the interval. So to find the possible values where our local maximum and minimum might occur, we could use the fact that we know that the first derivative is 0 anywhere that we have these critical values. And if we use those numbers plus the endpoints and we test them, we should be able to figure out the absolute maximum and the absolute minimum. So here's our closed interval method. To find the absolute maximum and minimum values of a continuous function f on a closed interval AB, step 1, find the values of f at the critical numbers of f in the interval a to b. So recall that critical numbers come from setting the derivative equal to 0. So we have to find the first derivative, we have to set it equal to 0, and we have to solve for x. There's a lot of steps there in part 1. Then, step 2, find the values of f at the endpoints of the interval. And then once we've evaluated the critical numbers and the endpoints, after we've evaluated the function at all of those x values, the x value that gives us the biggest value is obviously our absolute max, and the x value that gives us the smallest value would be the absolute minimum. So let's give this a try. For the first problem here, we are given the function f of x is equal to x cubed minus 6x squared plus 9x plus 2, and we are given the interval -1 to 4. So this information right here, these are my endpoints of the interval. Okay, so I already know my endpoints. Now I need to find the critical values, which requires me to find the first derivative. So f prime of x is going to be equal to 3x squared minus 12x plus 9. And I want to know what values of x make that first derivative 0. So if I set this equal to 0 and I factor, first I can take out a GCF of 3. So then I'll have x squared minus 4x plus 3, and then that trinomial is an easy factor. That's going to factor into x minus 3 and x minus 1, which tells me that my critical values here are going to be x equals 3 and x equals 1. Okay, so now I am going to take my endpoints, which were -1 and 4, and I'm going to take my critical values, which are x equals 3 and x equals 1, and I'm going to plug all 4 of those values into my function f of x. So I am going to find f of -1, f of +1, f of 3, and f of 4. And I'm just going to do the math. So f of -1 is going to be, and again, make sure that you are plugging these into the original function and not into the derivative, okay? So f of -1 is going to be -1 cubed minus 6 times -1 squared plus 9 times -1 plus 2. And if you trust my math, when you grab your calculator, you get -14. Next, we're going to plug in 1. So 1 cubed minus 6 times 1 squared plus 9 times 1 plus 2. You do the math and you get 6. Next, we plug in 3. 3 cubed minus 6 times 3 squared plus 9 times 3 plus 2. We get 12. And then finally, when we plug in 4, 4 cubed minus 6 times 4 squared plus 9 times 4 plus 2 gives me an answer of 16. All right, so what did I just learn? Well, I learned that when x is -1, the value of my function is -14. This is going to be my absolute minimum because it is the smallest value of the critical values that I plugged in. And f of 4 gives me 16. This is going to be my absolute max value on my interval because it is the highest y value that I got when I plugged in my critical values. Let's try another example, same idea. So in letter B, again, the interval is -1 to 2, so these are my endpoints of the interval. So those are going to be 2 of the values that I'm going to be plugging in later. And now I have to find the derivative of my function. So f prime of x is going to be equal to, this is going to be chain rule, because I've got something cubed, but the something is a function in itself. So I bring down the 3. X squared minus 1 stays the same. The exponent becomes a 2, but now I have to multiply by the derivative of x squared minus 1, which the derivative of x squared is 2x. The derivative of -1 is 0, so just 2x. And I want to know where this is equal to 0. Don't multiply it out. That's just more work for you. X squared minus 1 squared, keep in mind, is x squared minus 1 times x squared minus 1, because there's 2 sets of x squared minus 1. And x squared minus 1, we know, is a difference of squares. That factors into x plus 1 and x minus 1. So we get x plus 1, x minus 1, x plus 1, x minus 1, and 2x. And so now the next step is, what are our critical values? Well, those are any values that make those factors 0. So in this case, -1, +1, and 0 from the 2x. We get a 0, right? So -1, +1, and 0. And our endpoints are -1 and 2. Well, -1 was also a critical value. So we have to check f of -1. We have to check f of 0. We have to check f of 1. And we have to check f of 2. And so when we plug these in, we get, let's see here, in the first one, we get -1 squared minus 1 cubed, which gives us 0. When we plug in 0, we get 0 squared minus 1 cubed, which gives us -1. When we plug in 1, we get 1 squared minus 1 cubed, which gives us 0 again. And when we plug in 2, we get 2 squared, which is 4, minus 1, which is 3, cubed, which is 27. So what is the lowest value we found here? Well, that's -1, right? So we have an absolute minimum here. When x is 0, it produces an absolute minimum of -1. And our absolute maximum is 27, and that occurs when x is 2.